Hi, this is ET250 Lecture 12. As we stated in the last lecture, we're going to begin our discussion on transient circuits and transient behavior. Today, we'll look at how capacitors behave in a transient condition. And so we're going to look at a simulation and an RC or resistor capacitor example. And then we're going to introduce this new math. I know it might seem scary, but it's really not that bad. It has to do with first order differential equations, but don't be intimidated. I'll walk you through everything. We're going to review e to the x. So we're basically assuming you guys are intelligent but unfamiliar, okay? And so e to the x is that nice log number 2.78, blah, 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 blah. We'll go over a solution to a differential equation. This is the special form or guess, k1e to the st plus k2. And I know this might seem scary, but don't worry about it. This is just the derivative of this, right? The nice thing about e to the x, if you take the derivative, it's itself. So look at this, constant goes to 0, but sk1e to the st. We'll see this later. We'll look at boundary conditions. So VC of 0 minus, VC of 0 plus, VC as time goes to infinity. And I know all this might seem like, what's going on? This is a little crazy. Don't worry, I'll explain everything. We'll talk about time constants. This is a very important concept when figuring out how fast a voltage charges up or discharges. It's the time when when you get a -1 in your exponent here in your solution. And then another property is that the initial value divided by time constant will be the initial slope of some of these plots. And then we'll go over into another example in simulation. So I know this might seem like a lot, but I'll walk you through everything, don't worry. Okay, so let's begin. Transient circuits. And right now we've only studied DC systems when I and V are constant, no changing, right? No switches or anything. But we want to have a better understanding when we do get a change in state. And so here's a simple example. So imagine you have a capacitor, you have a switch, and you have a resistor. And when the switch open, no current is there. Okay. And so we can consider this steady state. So everything's constant, right? So now I have this switch and we can see, let's assume that the capacitor is charged. So there's some non-zero voltage on here. So somehow this already had some voltage across it, maybe 5, maybe 10 volts, something like that, okay? And now, if we close the switch, I think you guys can already imagine what's happening. Remember, our capacitor we've modeled or thought of as a spring, an elastic membrane. So it's charged now. Once I close this switch, it's going to release that energy and dump that energy into the resistor, right? And so in the transient state, now that current is positive, this resistor gets hot, of course, all that energy goes to heat, but this voltage is going to be decreasing because the pressure is releasing off into this resistor and burning off as heat. Okay, so the VC is changing, the voltage here is getting smaller, the current jumps up and then also decays or heats up. Now, if you leave the switch closed for a long time, let's look at what happens. The current now goes to 0 again, right? So it spiked up and then went to 0. And the voltage now in the capacitor has discharged to 0 in this case. And we're back to steady state. So this is going to be a common theme in a lot of the example problems you'll see. You'll have steady state, you'll have some transient, and you'll have another steady state. Now you could go from steady state to transient, and then transient to another transient, depending on a second switch or whatever different action. But if you leave these systems by itself for a long time, it'll steady out to a steady state condition. So let's switch over to the computer and see a simulation of this. Just this behavior here. So I'm going to go over here and switch to my computer. And what we see here is the similar setup, right? I have a capacitor here on the left, or in the middle, I should say, and I have a resistor. And notice these things are voltmeters, right? And here's a voltage source and a resistor just to charge up the capacitor, right? Because in simulation, I need a way to charge this capacitor. So right now, remember we are in steady state, nothing's happening, no current's flowing, the capacitor is behaving as an open circuit. No currents flowing through the resistor. The voltage across here is 0. So that by KVL, these two voltages are the same. So this has 5 volts 5 volts across this capacitor. Now, when I close the switch, it's exactly the situation that we just saw. the voltage is on the capacitor is going to dump the current all the way through the resistor. It's going to dissipate, and we're going to see this current rise and the voltage rise, and then decay off to zero. Okay, ready? Let's do it. Perfect. And so this here is a plot of the voltage, and you can see that the voltage in the resistor spiked up to be 5 volts, right? You can see that 4.995 volts, and then decayed off. Okay, and so we can do that again. I can go over here, I can charge up, quickly charge up the capacitor, and then dump that energy, right? Cool. So I hope this is a nice intuitive simulation showing the behavior of a capacitor and a resistor interaction. All right, cool. So let's go back to the document camera. Okay, so to continue on, this is the same plot, right? We had our steady state condition. This voltage that we're plotting right now is the voltage of the capacitor. Okay, yep. And we can see here that initially for the capacitor, it was 5 volts or whatever non-zero value it was. And then once I closed the switch, you had your transient state. And then if you left it alone for some time, then the capacitor voltage discharges 0 and we're back to steady state again. Okay. Now, the question we might have is, can we show this mathematically, right? Because what's happening is there's some calculus and differential equations that are going on. We want to uncover that and see if we can model it on our own. Okay, so here's a closer look at that example. We have a capacitor, we have a switch, we have a resistor, and let's say we give it some values. Let's say we have 10 volts and 3 ohms and 0.01 farads, right? And we want to find a mathematical expression for VC of t, and then we'll plot it. And we should get this, okay? We should be able to plot this in our heads, in fact, right? And that's actually something I'm going to want you guys to do, is even before you do the math, just think about it for a second. Well, where would all the electrons want to go, right? Where would all the charges want to go? How would current want to flow? Where's the pressures, right? And think about that intuitively first, so that when you do get the mathematical result, it matches your intuition. All right, okay, so before the switch closes, let's remember everything's in steady state, no current. Well, just because something's in steady state doesn't mean that the current has to be 0. It means the current's not changing. So I just want to make sure that you guys have that distinction, all right? In this case, the current's not changing and it's 0. But in a general case, a steady state means it's not changing, not necessarily 0, okay? We'll say that this VC is 10 volts and is constant. And we know after the switch closes, we get the transient conditions, and I and VC will not be constant. Okay, so now let's draw it with the switch closed. Okay, when the switch is closed, now we can start incorporating that capacitor equation. That's why we have these differential equations, because the capacitor equation has a dVC dt in it, right? So remember our passive sign convention. In this case, the way we've drawn it, the current is leaving the positive terminal of the voltage. So therefore, we're going to use the minus. I equals minus C dVC dt. And on this side, we have our good friend Ohm's law. VR equals plus, because the current is going into the positive terminal, IR. Very good. And we can easily smash these together, because KVL by KVL, VC and VR are the same. And so that means that VC equals to negative C dVC dt, right? Because the VC goes there and this guy goes in here, okay? So look at this. We have an equation where we have VC and its own derivative in the same equation, right? It's kind of like one equation, one unknown, right? But not quite, because we have the derivative form, right? Isn't that weird? VC equals the negative derivative of itself, or scaled negative derivative of itself. That is kind of weird. Okay, and then the question is, how could we plot this? If I wanted to plot this VC of t, but then it has its own derivative of self, it's a little tricky, right? But what we'll see is we're going to introduce or reintroduce and review that nice exponential, because remember the e term is the nice special property of the e to the x is that you take the derivative, it's actually itself. Well, that's going to show up here, okay? So we're hoping that we get a mathematical expression that describes this plot. Okay, so let's not get lost in the sauce. This at the end of the day is what we're shooting for when we get an expression for VC. Okay, so we want to see a mathematical expression that's going to give us this plot for this example. Okay. So let's keep going. How do we deal with this? So we're gonna have to take a little detour into some math land, and then we'll resurface. Okay. So keep this example in your mind, and let's look at this math tool. So we're gonna solve a first order differential equation. You might look at that and you go, God, first order differential equation, that is one scary line, right? Well, first order, second order, third order just means the number of derivatives. In this case, what do we have? One derivative. So this is about the simplest differential equation you have, right? So this is a first order, and it's differential because you see a derivative. So first order differential equation is an equation with a derivative, with only one derivative. Maybe that's a way to easily, maybe to say it in a less scary way, okay? All right, so this is basically what I just stated, just an equation that has a variable and its derivative. The first derivative is the same. So a second order differential equation, you would see a double derivative. Those are a little scarier. They have sines and cosines and whatnot, but we're not going to deal with that today. Okay. All right. So we want a VC of t without its derivative, right? And like I said, a little foreshadowing, we are going to use the nice math entity e to the x, because if you take the derivative of e to the x, you get e to the x. Super cool, right? That is why the number e, I mean, that's like the definition, right? The derivative of e to the x, there, the 2.78 number, this is a special number because of this property, right? That's where that number comes from, right? Because if the number was 3, it wouldn't behave like this. If the number was 2.6, it wouldn't behave like this. It gets close, but this is the special number that if you take the derivative of 2.71828 blah, 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 blah to the x, you get the same number to the x. Very, very cool. Okay, what does e to the x look like if you were to plot it? Well, it looks like this. At e to the 0, you get 1, right? This should be, review. Your eyes should be glazing over at how boring this part is, right? As you increase x, the number in the exponent, you just get bigger and bigger and bigger, right? In this direction, this is e to the negative x, or negative values, right? Okay, no problem. All right, we will actually be dealing with over here, okay? So then if you do y equals e to the minus x, what are you doing? You're just flipping this, right? Okay, just flip about the y-axis. So we're going to be living kind of in this territory. Notice this is already looking like the plot we just had, right? Okay, so then what else? What other review can we look at? Well, what if we wanted to show a rising? So look at this. This is a falling. This is going to be like a voltage decaying. What if we wanted to show a voltage rising? Well, we could add a negative here. Look at this, right? Look at this. This is a rising. And what if we wanted to bring it up so this point goes to 0? Well, we just add 1 to this equation, right? You can see how we can shift it up. Can you see how this would be like a rising voltage? This would be like a falling voltage, right? And we can easily scale it, right? How would we scale this? Well, we could multiply a constant, right? How could we change the rate at which it increases or decreases? We could put a little number in here, right? So putting a number here, here, and here can change the scaling and like the squish factor of this, if that makes sense, okay? All right, and so here's an example of different squish factors, right? So this y equals e to the minus x should look like this one here, right? And if you have a bigger number, y equals minus 1.5, you're going to get a steeper line, right? A steeper. And if you have a minus 0.5, which is less than 1, you're going to have a shallower line, right? You guys see that? Shallower. Okay, so that number in the exponent changes how fast this decays, right? Okay, now what about these numbers here, right? So if you have something general, what you can have is something like this. Well, this is let's plot this. So 3e to the minus 2x plus 5. Well, we could look at this. What is x when this is 0? Well, this becomes 1, 3 plus 5, so we get 8, right? And be careful, it's not 3. It's tempting to be 3, right? But you had this extra kind of number here on the side. You had to add to it. Okay, what about when this goes to infinity? E to the minus infinity, this makes this whole thing 0, so this decays to 5 in this special case, right? And then the 2 here changes the steepness of this, right? So this 2 would make it steeper than if this was 1, all right? So I hope that this, this form, there's going to be like 3 numbers here that will dictate all sorts of e to the x kind of shapes, right? It's the constant in front, the added constant on the back, and then the constant that multiplies the exponent, right? Okay. Now, another thing, just to review, like I said, I'll walk you through everything, don't worry. If you took a derivative of e to the ax, and let's say a is a constant, that's pretty easy. You just pull the a out, right? Derivative of the top, you know, chain rule here, a e to the ax. Okay, very good. If you take a derivative of this with a constant in front, that's not too bad either, because you just multiply, you got a e to the ax times the constant, good. What if you took a derivative of this with an extra constant added? Well, that's easy too, because it's just the same as that one, right? The c, the derivative of constant goes away. Okay, so none of these, I think, are too difficult. If you just spend some time looking at it, it's not too bad. What about this one? I just add a little negative sign. Well, the negative sign just comes to the front. Okay, no problem. So none of these, I think, are an issue. It's just we're reviewing it and kind of brushing off the rust from maybe a year ago. Okay, now let's go back to the example. So we go all the way back to the example. Okay, so we're all the way back here. I'm gonna put these pages on the side. Okay, we're back to the example, and we had our capacitor discharging into the resistor. We came with this, combining the capacitor equation, Ohm's law, KVL, and we got this. And remember, we want VC as a function of time, not its own derivative. And we're gonna have to use that e to the x kind of form. And so look at this. We can take a guess. We can have a K1 e to the s K2. We don't know what K1, K2, and S are, but we could imagine S, K1, and K2, if we could find them, they would match this relationship because the derivative of this will be some form of itself, right? Let's see here. And then here's taking the derivative of this. If I take the derivative of this, what do I get? S K1 e to the st plus 0, right? Because the derivative of this is 0. S K1 e to the st, okay? All right, so we know that this has to be the answer. We don't, or the form of the answer. We don't know what S, K1, and S and K2 are, but we know this has to be the form of the answer for these special first order differential equations, right? Does that make sense? I hope that makes sense. Okay, so then the question is, well, how would we solve for those 3 numbers, S, K1, and S2, with the information given? Well, the first thing we could do is just take it and plug this guess into our first order differential equation. So I'm going to plug this into here. Okay, so check it out. I'm going to put in K1 e to the st plus K2. And for the derivative part, I'm going to plug this one, SK1 e to the st. Now, I have one equation here. And it might seem like I only have one equation, but really sneakily I have 2 equations. And here's where the 2 equations are. I have one equation where I can pull out everything that's attached to the e to the st terms, and I can pull out an equation where I have everything that's attached to non-e to the st terms, right? And in this case, what do we see? The ones attached to the e to the st are K1, and then this minus RRC SK1. And the ones that are not attached are just K2 by itself. Not too bad, okay? So if I look at the first equation, K1, yep, good. Minus RC SK1, good. And they equal each other. So that's kind of nice because I can see immediately K1 cancel out. I could solve for S. S equals minus 1 over RC. These are terms that are from the system. This is that unknown S. Okay, what about the second term? Well, K2 equals 0. Oh, that's kind of nice. In this special case, K2 equals 0. Not always going to happen, but in this case it is. All right, so I've solved for 2 of the 3 unknowns in this general form. Okay, so I know this is minus 1 over RC. I know this is 0. And so the question is, what is this? All right, okay, so we still need K1. Well, now we can use this concept of boundary conditions. And the boundary conditions are, well, what's the voltage at time 0? What's the voltage at time infinity? And if we go back to our system, the voltage at time 0 when the thing was open, right before was 10 volts. Okay, that was the given. And then the time we know as it goes to infinity is going to steady out to 0, right? 0 volts. So these are two nice boundary conditions, right? And so what we can do is go, okay, well, we know we're almost there. We have Vc equals K1 e to the st. We know what S, we know what K2 are, and we know the boundary condition. So that means we know a time and value, and we can plug it in and see if we can solve for K1, right? So how do we do that? Well, we put the time and we put the value, right? And now we have one equation with one unknown. So we're going to put a 10 in here. We're going to put a 0 in there, right? Since we're using this boundary condition, we're going to say this is 0, and now we don't know this. We can solve for it. If we use the infinity, well, we would have to put an infinity in there and then whatever the final value, but we use the 0 boundary condition. And it looks like in this simple case, look at this, at 0, e to the 0 goes to 1. We knew K2 goes to 0 already. This is 10. Oh, K1 is 10, easy. All right, and that should make sense. The VC at 0 time is 10 volts. That's consistent. And if we plug everything back into the equation, what do we get? We get this. V1, we know that this was the form that we were looking for. And now we can put in all the numbers. The initial voltage, e to the minus 1 over RC, that was S. K2 was 0. And now we can put the numbers that we were given. The resistance was 3. The capacitance was 0.01 farads. The voltage was 10. And we get 10 e to the minus 33.33 t, okay? And we can plot it. And if we go back and review our plots, we have a negative exponential, so it's going to fall. Remember, if we go back to our review on, oops, sorry about this. If we go back to our review, a negative exponential, e to the minus x is going to have this decaying, good. This point here is the initial scaled point, 10. And because we don't have any added part here, it's not, it's translated up or down. So we get the plot we were looking for, we intuitively figured out. So that's kind of nice. We have a way of creating equation from the math, and now we can, with this equation, we could pick any point at any time and figure out what the voltage is going to be, right? And so that's a very useful tool as an engineer to be able to now plot exact numbers, okay? All right, let's keep going. So the other thing I want to introduce to you was a time constant. And so time constant is a unit, physical quantity of time, right? We use the symbol tau, and it has a unit of seconds, and we know what seconds are. And the question is, well, what is it? And what it is a metric for how fast a first order differential system responds. This could be heat, like a room responds in a first order way. So like heating up a room, you'll see like this, heating and cooling a room. And so the time constant is basically how long it takes for the system to reach 63.2% of its final value. Okay, so from here to let's say about there, that's the time constant, if that makes sense. And the 63.2% seems like that's a very weird arbitrary number. Why did you come up with 63.2? Well, it coincides with the time it takes to get to e to the minus 1. So what is the time in this case to make a minus 1 in here? Well, you can easily see it's 1 over 33.33, right? If that makes sense, right? So in this case, 1 over 33.33 is the time constant for this system, okay? The other property of a time constant is that the initial value divided by the time constant is actually the initial slope. So in this case, 10 divided by 1 over 33.33 is the initial slope, right, of this system. Okay, so that's why a time constant is kind of useful. It has a lot of information embedded in it for first order systems. Okay, so let's look back at our system. So we had this nice equation, Vc equals V0 e to the minus 1 over RCT. What's the time to get the minus 1 in here in our system? Well, it's just RC. Oh, that's kind of nice. If you have a resistor capacitor system, the response time, right, the time constant, is just the resistance times the capacitance. That's kind of nice, right? So this might be good for memorization, and this might change for inductors, right? And you can see if I plug in RC over RC, I get minus 1. Good. Okay, you could rewrite this differential equation as, instead of V naught e to the minus 1 over RC, then you could write it as V naught e to the minus 1 over tau times the time, right? It's the same thing. Okay, and notice the units cancel. That's nice. time and time, you get a unitless number in the exponent. That's a good thing mathematically, right? Because what does it mean to raise something like e to the seconds or e to the volts? That's weird. You want these terms to be unitless. Okay. Okay. So as I said before, we want t to be the 1 over, right? And so look at this. V naught is 0.368, right? That is right here. If I have e to the minus 1 here, I get V naught times 0.368. Well, 0.368 plus 0.632 is 100% or 1, right? So e to the minus 1 ends up being this 0.368 number, right? And you can see this is the time. If the time was RC, you get e to the minus 1, and you can see this is the time where we've fallen 63% or we've come close 63% to the final value. In this case, the final value is 0, right? All right, let's keep going. Okay, now another burning question I'm sure you all have is R and C a unit of seconds? Right? Because it seems like you're making that claim that R and C is a unit of seconds, right? And what's R and C? Well, you have an ohm and a farad. That's a weird combination. Is that true? Well, where can we get ohms from? Ohm's law. Where can we get a farad from? Our capacitor equation. So ohms is volt over amp, and a farad is a amp second per volt. Okay, so let's multiply them together. Volt over amp times an amp second per volt. Cancel, cancel, cancel. Yes. And RC, resistance times capacitance, is actually describing seconds. Very cool. All right, let's do another. Oh, yeah, sorry. This is to finish off the justification that the initial value divided by the time constant is the initial slope. So let's see if that's true. So the slope of that previous equation, you took the derivative, is the derivative of this, V naught e to the minus t over tau, right? And if I take the derivative, look at this, I get minus 1 over tau on the outside times V naught e to the minus t over tau. And if I put t equals 0, that's the initial time, what do I get? V naught over tau, right? So this is the initial slope. At time equals 0, the initial slope is minus V naught over tau. Okay, cool. So hopefully that convinces you that this fact is true. All right, so let's do another example. So here we have a voltage supply. Here we have a resistor, we have a capacitor. They give us these values and they tell us that the capacitor is discharged initially, VC of 0. And notice I put VC of 0 plus here. And so this is going to be the voltage right after the switch closes, all right? All right, so we're gonna find and plot VC of t, right? At t is less than 0, the switch is open when I close it. Okay, and it's given that the voltage is initially 0. It could be a non-zero value. It could be like 3 volts, 10 volts. It could be 110 volts, right? It could be bigger. But right now we're just saying it's 0 just to kind of make it easy for us. All right, so it closes and I want to figure out what is our intuitive plot. Well, what's going to happen? This thing's probably going to charge up, right? Okay, and so it's going to charge up like so. And let's see if we can, again, turn the wheel and get that same, what do you call it, thought. So look over here, let's double check. So we redraw, we're going to redraw with a closed. We have a resistor, capacitor, and voltage. And I also have my same current. Okay, I have the same levels of VC, and now I even added an intermediate dummy variable VR. Okay, now we're going to apply our 250 analysis. I have my Ohm's law. Oh, I have my new Ohm's law for a capacitor, I equals CD VCT. Is it positive? Yes. Is this positive? Yes. Okay. I can do a KVL minus VS plus VR plus VC, great. And I can start punching everything in, right? The Ohm's law punches in here and the VC, well, the VC's here. What about the I though? Oh, the I is the capacitor equation. Nice. And what do I notice? Lo and behold, I got a first order differential equation. I know VS, I know R, I know C, and I have a VC with a derivative. Notice this is a different, slightly different than the previous one we did, okay? So what can we do? We can go, well, I don't know what VC is. I could solve for it, but I would still have its own derivative, but I know that the guess, what is it? K1 e to the st plus K2 is gonna be valid, right? It's gonna be a valid solution for VC and its derivative. So I can punch that guess in. This was our guess, right? And I'm going to bring it into that equation. Okay. And so when I bring it in the equation, I know it gets a little bit messy, but let's follow here. Minus Vs plus Rc times sk1 e to the st plus k1 e to the st plus k2. Okay, so that's our guess here. And now let's see what we can solve. Remember what I said, all the terms with e to the st we can pull out. So nope, yes, yes, no. So I have a K1, I have an RC SK1 good plus equals 0. Oh, nice. Just like before, the K1s happen to cancel and I solve for S. Don't forget, this is a 1. It's a common mistake by students to cancel this out and make it 0. And then you say S equals 0. No, 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 no. K1, if I divide everything by K1 here, I get a 1, right? Okay, so that cancels to a 1. And so if I bring this over, I get 1 divided by RC negative. Good. Okay. Now over here, I get not everything without an EDST, negative VS, and K2. Good. And so K2 equals VS, right? Good. So I have S and K1, K2, and I still need to find K1 now. Like I said before, we can use our boundary conditions. So what's the boundary condition for this capacitor? Well, in this case, the initial voltage was 0. Great. So I can now plug it in here. 0 time, 0 volts. K1, K2. Well, this is 1. So what does K1 have to be? Well, K1 has to be K2. But in the previous one, K2 was 0. But in this one, K2 is just Vs. So that means K1 equals negative Vs if I bring it over. Nice. I have my answer. Vc is equal to negative Vs, right? Negative Vs because of this K1 here, okay? And e to the minus e to the s, which is minus 1 of RC, plus K2, which is just positive Vs. And you might look at that, you don't quite have the intuition yet for what this looks like, but it better look like that rising voltage plot, okay? We can plug in all the numbers, but what we end up getting is this, negative 100 e to the minus 10 to the 3 t plus 100. So here's the resistor value, here's the capacitor value. You have 100 times 10 to the 3 times 0.01 times 10 to the minus 6. Let's see, could we even slow down and figure what this out? 100 times 0.01, that's 1, right? Because this is 100, yeah? And 10 to the 3, 10 to the minus 6, that's going to be 10 to the minus 3 on the bottom, and then I can bring it up 10 to the positive 3 on the top. Good, okay. So this is my equation for the capacitor in our system, okay? So that's the equation for this capacitor. And let's plot it. So at t equals 0, what do we get? This becomes 1, and I get minus 100 plus 100, 0. That's good. At t goes to infinity, what does this become? 0, and I get 100. And so I should see this rising, right? With this rising, check it out. And what's the time constant? Well, the time constant is just RC, right? Which is just the 10 to the minus 3, right? It's the inverse of this, 10 to the minus 3. So 10 to the minus 3 is 0.001. So that means in 1 millisecond, I'm going to rise up to 63 volts, okay? So this hopefully matches intuition. Let's check out a simulation to see if this matches. So we're going to switch over to this. Okay. So if we go over here, we have the similar situation. We have 100 volts. We have the capacitor and we have the resistor here, and I'm measuring the voltage. It's 0 volts. Okay. All right. So if I click this over, oops, I got to run it first. If I click this over, notice we get that nice result, and I'm going to stop it right there. Okay. So you can see the voltage in this capacitor rose from 0 to 100 volts, and it took some time to do so. Now I can go into the properties and check out, I can change the milliseconds. So I have 100 microseconds per division, which is 0.1 milliseconds. So 10 of these is 1 millisecond. We said that 10 of these 10 of these divisions is 1 millisecond. So if I go from here to here, this should be 1 millisecond. Look at the voltage, 63 volts, right? So that's matching our time constant, right? So in 1 millisecond, which is 10 of these little blocks, I get 63 volts. Okay, and then here we can run it again. So run it again. I'm going to open the switch. I'm going to reset it. Okay, reset the simulation, and notice I have the same values in here. When I hit this voltage is going to rise, right? And the voltage in the capacitor charges up, and then there's no current. We're back to steady state again. Okay. All right, well, I really hope this lecture helped you, and I look forward to seeing you guys in class. All right.